Snap my finger right there. There we go. Okay. So, why am I showing you this? So first off, so there are about 320 of you between the first lecture and this lecture. 287 people filled it out. So that's like the overwhelming majority of you all. So this is a pretty good, these questions should give you a pretty good sense of how we feel. Okay, so first off, have you taken a physics class before? So a slim majority of you said yes that you have, but a huge majority of you said no you haven't. So what does that mean? That means if you are sitting and you have not, if you're sitting in your chair and you have not taken a physics class before, then chances are either the person on your left or the person on your right hasn't either. At least one of them, right? So why is that important? It's important because if you haven't taken a physics class before, it's okay. It's okay because there are lots of people that you can work with. Right? There are lots of people who also haven't taken it who are in the same place as you. I want you to remember that. But the more interesting question, in my opinion, the more interesting question is this one. Would you say you are more worried about your grade in physics than you are about your grade in other classes? A significant majority of you said yes. So 62% of you said, yes, you are more worried about your grade in this class than your grade in other classes. Now, why am I pointing this out? I'm pointing this out because, there's 17% of you who are like, yep, I'm fine. Great. If you're in that 17%, awesome. But if you're not, right, either you're like, yeah, I'm definitely more worried about my grade here, or not sure, which is, 85% of you, roughly, right? You're in good company. Right? There are a lot of people who feel the same way. It's okay to feel that way, right? But the class is designed around the idea of collaborative learning. It's designed around the idea that working with people to learn something is easier than working on your own, right? And so again, if you're feeling a little scared, feeling a little lost, whatever you're feeling, there are plenty of people around you who are feeling the same way. So that's why I really encourage you, what's DL all about? Spending time with people who feel the same way. You can study for quizzes together. You can work on your F&Ts together. All that good stuff. So I just want to let you all know that this is what's going on. Okay? Okay, so that's what I have to say about that. By the way, why am I masking today? I didn't lecture without a mask on. So I either have allergies or a little cold. I know it's not COVID, for sure. I have tested. But I have allergies or a little cold, and I want to, if it is a cold, I want to avoid giving it to anyone, so that's why I'm wearing a mask. That is one thing that I think is going to be really positive about the last 2 years, is even if we live in a world in, say, 20 years where COVID doesn't exist, I think it makes sense that if you're in a public space and you're sick, mask up for sure. It's nice for the people around you. So again, I don't actually know I'm sick. There's a lot of people with allergies right now, and I very well might be one of them. Allergies are worse in Davis than any other part of California I've been in. And I've been in a lot of places in California. So anyway, that's why I'm wearing this just in case. Okay, so I'd like to start here. I'd like to start with our fun physics since we just took a quiz instead of jumping into the actual topics. So this is something I said last week. Right? You don't need to, in case this needs to be said, you do not need to take notes on this. You can if you want, but you don't need to. This is what I said last week. This raises two really interesting questions, and it's these two questions. One, how do we know how the distance to faraway things like galaxies? Okay. Second, how do we know they're moving away from us? These seem to be two really obvious questions. If I'm saying this is true, then we better be able to answer these questions. Now, I'm not going to answer this one today. I'll try to come back to it sometime in the next couple of weeks. I would like to talk about this one because it's kind of fun. And I'd like to do it by telling you a story about this woman. So this is a star. She is also a star of a different kind. She is a physics star. Her name is Henrietta Swan Leavitt, and she was doing astronomy way back in like the early 20th century. So this is like, I don't remember exactly when she was working, but we're talking like 1910s, 1920s, something like that. And she was interested in not this specific star, but stars a lot like And I picked this star because it's a pretty picture. This is a really nice picture. This star is about 6,000 light years away, so basically next door. As far as we're concerned in astronomy, this star is literally just down the street. It's here in the Milky Way galaxy, but it has this special property. There's something really special about it. To do that, we got to play it forward in time a little bit. And what you're going to see about this star is that this star actually changes its brightness over time. Now, you may have heard it said that stars do not actually twinkle, and that's half true, right? So if you see a star twinkle, what's actually happening is there's stuff happening in the atmosphere that's distorting the light that makes it look like it's twinkling. So stars don't actually twinkle, but they kind of do a little bit. It's just that the twinkling happens instead of over seconds, it happens over minutes, or days, really, days and weeks. So the question is, what did Henrietta Swan Leavitt notice about these stars? Well, these stars are a type of star called Cepheids. And every star, at some point in its long lifetime, over hundreds of millions or billions of years, including our sun at some point, although not for a while, does this. And what she noticed was this, what's now known as Leavitt's law, that the dimmer ones pulse faster than bright ones. But this raises the same question that we already had, right? How did she know this? How did she know that her dimmer one was not just a bright one far away? Or that her bright one was not just a dim one nearby? And the way that she knew is because she was interested in looking at these two little, look almost like little clouds. But they're not clouds. Actually, they're called the Large and Small Magellanic Clouds, actually, now that I think about it, yeah. So they are clouds, but they're not like clouds on Earth. So these are, you can't see these, unfortunately, from the northern hemisphere. But if you go to the southern hemisphere, you can actually see them with the naked eye. They're actually pretty bright. And the reason they're so bright they're actually circling us, circling the Milky Way. They're little tiny galaxies, way, way smaller than ours, that just got caught near the Milky Way, and they're kind of going around it forever. And so what did Henrietta Swan Leavitt do? Well, she said, well, let's just assume that all the stars here are basically the same distance away. Is it exactly true? No. Is it approximately true? Yes. How many times have I said that already in this class? Is this thing exactly true? No. But if we assume it's approximately true, you can learn some things. And so that's what she did. And there were something like 50 or 60 of these Cepheids, these pulsing stars that were known in these clouds. And at the time, this was a time before computers. And let me tell you, how people did astronomy without computers is absolutely beyond me. Because what would happen is they would just take a ton of pictures, and then people would just sit down and stare at those pictures and measure each individual thing in the picture, and then move on to the next picture and measure each individual thing in that one, over and over and over and over again. It was exhausting, no doubt. And unfortunately, the way it usually works is you had the astronomer, who was always a guy, who would hand the pictures off to somebody else to do all the grunt work as they saw it. Henrietta Swan Leavitt was the person that the pictures got handed off to, but she made this discovery on her own, which was this. The dimmer ones pulse faster, than the bright ones. And this is amazing because of this. If we know how bright something is and how bright it looks, we can figure out how far away it was, how far away it is. This second part is easy. The second part is easy because we just look at the sky and we see it and we say, this is how bright it looks from here. This first part is hard, but Henrietta Swan Leavitt had figured out how to get the first part. She'd figured out how to get the first part. So, unfortunately, she passed away before this discovery was made, but later on, this guy, Hubble, the guy we talked about last week, used this fact that Henrietta Swan Leavitt had discovered to measure the distances of a bunch of really far away galaxies. And he discovered this. Almost everything in the universe is flying away from us at incredible speeds. The moral of the story is this: physics is often surprising. It often the universe doesn't like to behave the way we think it behaves. It likes to surprise us all the time. At the time when Leavitt was doing her work, basically scientists thought that we had figured out physics. And they were so wrong. Everything that's happened in the last 100 years, we knew nothing about at the time. And it has shook the way that we understand the universe and shook the way we understand our place in it. So she made that discovery. And at first it seemed like, it seems, if you just introduce it as like, oh, guess what? Some stars are brighter than others, and you can tell based on how fast they pulse. On its own, it doesn't seem all that incredible. It's an incredible discovery, but on its own, it's like, okay, that's cool, so what? But using that information, Hubble built on that and was able to discover something that truly shook the way we understood the universe. Now, of course, Leavitt did not get the credit she was due at the time. She wrote a paper on it. It was about 2.5 pages long, and instead of being included in the author list, it just said right at the top, this manuscript has been prepared by Miss Leavitt. Now that has been corrected. So the journal that it's published in still exists, and she is now first author in the author list, as she should be. But again, the takeaway is this, not that, although that is a cool takeaway. Physics is often surprising. And sometimes something that looks to be cool but not necessarily world-shattering turns out to actually be world-shattering, and this is one of those examples. So that's the first part of the story, the part about how we know how far away the objects are. The second part of the story, like I said, we'll have to wait for another day. How do we know how fast they're moving away from us? Okay. Any questions? All right. So let's move on to actual content for this class. So this is the stuff we need to take notes on. Okay. So let's start by talking about, just doing a brief recap of what we did last week. As usual, I should be able to let you out about 10 minutes early. So, what did we do last week? We talked about mechanical energies, right? So mechanical energies are energies that have to do with where an object is and how it's moving. The way I presented them was, these are energies that an object has that we need to know its relationship to other things in order to calculate. So for example, if you want gravitational potential energy, you need to know how high something is in relation to the floor. If you need to know kinetic energy, you have to know how fast the object is moving, right, related to something else. Okay? So the kinetic energy depends on speed. This is the one that we're probably most familiar with because we experience it in our day-to-day life. Gravitational potential energy depends on the distance from the ground. And spring potential energy depends on how far it's been stretched or compressed. Right? This is probably the less intuitive one because we're not as familiar with it in our everyday life, but it is one that you got to play with a little bit in DL with the springs and all that stuff. And these are the equations, right? These are the equations. One thing I would note here is that the kinetic energy equation and the spring equation look very similar in a lot of ways. I don't know if there's some deep meaning behind this. Perhaps there is. But at any rate, it may just help as a reminder of a way to remember the equations, although you don't need to remember the equations, right, because I'll give them to you. But perhaps you're in a situation, I don't know what the situation would be, maybe you're taking the MCAT, I don't know, where you're like, wait, I need to remember the spring potential energy equation, I can't remember what it is. Well, guess what? It looks a lot like the kinetic energy equation. So that's one way you can remember. And then, of course, we have the gravitational potential energy one. Gravitational potential energy depends on three things. It depends on the mass of the object. Heavier objects have more gravitational potential energy, which sort of makes sense because heavier objects are pulled harder on by gravity. It depends on h, the height above the ground, right? The higher an object is, the more gravitational potential energy it has. And it depends on this constant g, which is known as the gravitational acceleration. For reasons that are not really important right now, it is an acceleration, but it's not, we don't really care about that at the moment. G is usually 10, so we're mostly going to be working with gravitational potential energy with stuff that is near the surface of the Earth. So, you know, this object as it's falling, for example, something like that. But I could give you a problem on a quiz or on an exam where I said, let's imagine that G is different. Let's imagine that G is 3 instead. You're living in a world where G is 3. You're only 30%, you only weigh 30% as much as you do on on planet Earth. You can jump high and all that fun stuff. If you've ever seen those pictures of astronauts jumping around on the moon, right? Why can they jump so high? It's not because they magically got stronger in space. In fact, muscles atrophy when you're in space, as is probably not super surprising. It's because the moon just doesn't pull as hard on them. And we could think of that as G being less. So G on the moon is about 1.5, 1.6, something like that, instead of 10. Okay. So, one thing that I've been hearing from TAs and TA meetings is that you all are curious about this. How do we deal with things like friction and air resistance? And we haven't really talked about it yet. But of course, friction and air resistance are things that we experience in our everyday life all the time, right? Without friction, we couldn't even walk, right? Because if I'm going to move myself forward, there has to be friction here, otherwise my foot will just slide back, right? So friction is essential to just doing daily things. Air resistance is also important, although we don't really experience air resistance as much. So when you're walking around, it is true that you're experiencing air resistance, but it's pretty minimal. But it becomes really important when you think about things like cars. Cars move much faster than us. They're much bigger, much blockier than we are. And as a result, they experience a lot more air resistance. And a huge, I don't know the exact number, because it depends on the speed, but a significant fraction of the energy or the gas that you use is not actually being used to move the car forward, it's just being used to push air out of the way. Yeah, it makes those high gas prices hurt even a little bit more now, right? Like, you're just using half of it to just move the air out of the way. But that is what happens, right? The air is there, it's light, but we still have to move it. And so that's why air resistance matters. And so there's two ways that we can deal with this. The first one is friction and air resistance are forces that do not talked about work very much at all. It's just sort of been there. We're going to talk about it on the next slide. We'll get there. But the second option is friction or air resistance result in an increase in the thermal energy of the system. Right? That's the other option. So if you think about it, if you were to take your hands and just start rubbing them together like this, what you will notice is that your hands will start to get warm. Right? Why is that? It's because there's friction between your hands. Has anyone seen The Karate Kid, right? Yeah. There's friction in your hands. Is that an old movie at this point? Because I know they made a new one. I've only ever seen the original one, which is like 30 or 40 years old at this point. So it's kind of an old movie, I guess. Yeah? Huh? You saw the one with Jaden Smith?
I only saw the one with Jaden Smith.
Yeah, so there's an even older one, and I could not tell you who was in that movie, and it's been a long time since I've seen it. But there's this scene where Mr. Miyagi's like doing this to warm his hands up to help with a cramp or something. Why does this work? Because there's friction between your hands. And it turns out that friction tends to convert things like kinetic energy into thermal energies. Right? So these are two ways that we can think about this. We can think about it as air resistance are forces that do negative work, or friction and air resistance result in an increase in the thermal energy of an object. So let's talk about work here. So what is work? So up to this point, all we've said about work is just a way that energies change. Right? Work is just a way that energies change. We haven't talked about what work is or when it shows up. And this is where work comes into play. Work is done whenever a moving object experiences a force. So now we know why we saved work until we had talked about kinetic energy. Because you cannot have work if you do not have some sort of kinetic energy. You cannot have work unless you have some sort of kinetic energy. We'll see something in a few weeks where it's not totally obvious that there's kinetic energy involved, even though there's work, but I promise you it's there. But work is done whenever a moving object experiences a force. Now, a force is just a push or a pull. A force is just a push or a pull. We're not going to talk at great length about forces in this class. Most physics courses actually start with forces. And the reason for that is that forces were the first thing that we had a really good mathematical framework for. This was done by Newton in his famous Principia, where he casually invented calculus and then used it to describe forces. So that's where most physics courses start. You'll see them in 7b if you take 7b. Okay? For now, for our purposes, again, a force is just a push or a pull. The unit of the force is a Newton. which looks like this. Kilogram meter per second squared. Why is it that? Not important. But it has an interesting property. If we multiply this by a meter, we end up with 1 kilogram meters squared per second squared. Does anyone want to guess? Or maybe not guess, maybe you've seen it. What a kilogram meter squared per second squared is, yeah. It is a joule. It is a joule. So, if you have a force, 1 Newton, and you multiply it by something that's in meters, in other words, a distance, you get a joule. Which makes sense because work is an energy, right? Work is energy that is entering or leaving our system, and so it better have units of joules. So the takeaway is this. Work is just equal to the force that an object feels times the distance it travels. Work is equal to the force an object feels times the distance it travels. Now, while heat generally involves changes in internal energy, usually when you have heat, it's because you have something that's warm and something that's cool, and there's energy flowing between them. We call that heat. Usually involves changes in mechanical energies. Usually involves changes in mechanical energies. I'll come back to that in a second. So, but the question is this, though. Is that work positive or negative? Is the work positive or negative? And to think about that, let's think about what work is, right? Work is a change in energy. And so if the work is leaving your system with more energy than it started with, the work is positive. If the work is leaving your system with less than it started with, then your work is negative. So this is a way that you could think about it. Ask yourself this question. Is this speeding up my object or slowing it down? So let's say I take this object and I slide it across the floor, and it slows down and it comes to a stop. Why is that? Because there's friction on the ground that is slowing the object down. And so if we imagined describing the friction as a force at a distance, that would be negative work. That would be negative work. Why is it negative work? Because it's removing energy from the system. The kinetic energy of the system is going down as the friction is taking it out, as the friction is converting that from kinetic energy into thermal energy. But then there's the opposite. Let's say you have something that's been given a push and it's speeding up. Then what's going to happen? Then your work is going to be positive, right? We're putting energy into the system. Okay. So, let's look at an example. So let's say an object is sliding across the floor and experiences 25 newtons of force and travels 5 meters. How much energy is lost due to friction? We just take the force and multiply by the distance. 25 times 5 is 125 joules. Now, why did I point out how we determine whether it's positive or negative? Because I'm not necessarily going to tell you whether it's positive or negative. I'm not necessarily going to say explicitly it's positive or this work is negative. Friction is negative. Right? Just what does friction do? Friction slows stuff down. What do you think air resistance is? What do you think air resistance does? Speed things up or slow things down? It slows things down, right? That's why it's called a resistance. So air resistance is going to be a negative work. Now, in an example like this, it doesn't really matter because notice what I said. I said how much energy is lost due to friction. So saying just positive 125 joules would technically be correct as this question is worded. But what about the case where you have an energy interaction diagram and you have like 3 different energies that are changing, maybe you have heat, then it's really going to matter. Then it's really going to matter. And so you just have to ask yourself that question. Is this force helping my object move faster or is it slowing it down? If it's helping it move faster, it's positive. If it's slowing it down, it's negative. Okay, so I didn't actually show you, let me go back. I didn't actually show you this slide, but this was what I called this thing. It's called a hodgepodge of physics facts because there isn't a great theme to these slides. So that's friction, air resistance, and work. Let's talk about this. Okay, so this is sort of a new thing. It's not totally new. It sort of follows from what we were talking about, but not specifically. So there is this deep, deep connection between potential energy and forces. Now, I said we do not have to know a lot about forces, and that's true, but we need to know a tiny bit, and this is one of those things. Does anyone know what potential energy this is? What does it look like? I heard someone say spring. Yeah, it's spring, right? So how do we know it's the spring? Well, this is a good hint. Right down here. It says distance from equilibrium, right? That's a good hint that we know it's a potential energy, right? It says it's a potential energy. What potential energy depends on the distance from equilibrium? It's the spring potential energy. Not only that, but it's the right shape, right? It's a parabola. When an object has potential energy, it very often, though not always, will also be experiencing a force. So as an example, we have talked about falling objects a lot. Why? Because they're very easy to visualize, right? We see falling objects all the time. And the way that we have used to describe why an object falls is that it has some amount of gravitational potential energy. And then when we drop it, it chooses to, well, it doesn't choose, right? But it converts that gravitational potential energy into kinetic energy. That's the way we've described it. That's correct. Everything about that is 100% correct. But there's another way to describe it. And the other way to describe it is that the force of gravity is pulling on this object and causing it to accelerate downwards. And the reason that is also a correct description. That's the way Newton would have described it. There's nothing wrong with that description. There's nothing missing. They're different descriptions, but they get us the same result. So why am I bringing this up? Because there is a really deep relationship between force and potential energy, and the relationship looks like this. Now, there's calculus on the screen. You do not need to worry about calculus for this class. I know most, if not all of you, have taken it. I'm not going to be asking you to use this equation on a quiz or test. Okay, so don't worry about that. But we do need to think about what this means. Right? What this math means is the force an object feels will always be in the direction that causes its potential energy to go down. So again, let's hold this object and drop it. It goes down. Why is the force downwards? Because if this object moves down, its gravitational potential energy goes down. So because it feels a force downwards. And the faster the energy is changing, the stronger the force. So let's go back to this. What does this say? Right? It's a spring, right? And you've played with springs, and hopefully what you've noticed, or as you've been playing with the springs in DL, is that the farther you stretch them, the more they pull back on you. Right? The farther you stretch a spring, the more they pull back on you. How does this tell us that? How this tells us that is, let's say that we take this spring, it's sitting at its normal length, and we stretch it just a small amount, just a little bit. Right? What this plot says is that we'll be feeling a force back towards equilibrium in the direction that causes the potential energy to go down. Right? The spring wants to go back to its natural length. And this says, the fact that this gets steeper and steeper says that the farther we pull it, the stronger it's going to be pulling back on us. The farther we stretch it out, the more it's going to be pulling back on us. Right? One way I like to do this, nice little mental model that helps us, yeah.
When you just talk about the gravitation,
yeah.
Energy,
Yeah.
That the gravity push the pen down, or just pull the pen down?
The gravity pulls this down. Yeah. Does that answer the question? Yeah, okay. One little mental model I like to use here is imagine placing a little marble down right here. What is the marble going to do? It's going to roll down. So that works pretty well. And then what's the marble going to do when it gets here? It's going to be moving pretty fast, so it's going to roll up this side, but then it's going to slow down and come back. That's exactly what a spring does. It bounces up and down like this. It's not a perfect mental model. It doesn't get you all the way, but it gets you far enough for this course. Again, you do not need to do this calculation for this class. We're not going to ask you to do it. It's good to know that this is what it is, but we're not going to ask you to do it. Okay, so which potential energy is this? Which potential energy? Gravitational potential energy. What does this plot tell us about the force of gravity? Well, it tells us two things. What does it tell us about the direction of force? Well, it's always this way. Right? It's always to the left because that's the direction that causes the potential energy to go down. What does to the left mean on this plot? To the left means decreasing height. Right? That's what we know about gravity. When you hold it like this, an object like this, it feels a force this way towards decreasing height. It wants to get closer to the ground. What about the strength? What does this tell us about the strength of the force? Is it changing or is it the same? It's the same, right? The slope of this line is the same everywhere. It's a straight line, unlike this one, right, where it gets steeper the farther away you get. This one doesn't. And so the force of gravity, as far as we're concerned, is always the same strength, no matter where you are. Now, is this true in real life? No. The farther away you get from something, the weaker the force of gravity is, right? The sun does not pull as hard on Mars as it pulls on us, for a couple reasons. One is that Mars is a lot smaller than Earth. Okay, that's one of the reasons. But the other reason is that it's farther away. But for our purposes, when you're near the surface of the Earth, which is which is what our problems are going to be about, it is correct to say that the gravitational force doesn't change with height. It's basically the same. Right? But all that information is encoded in this plot. So this is the next fact in the little hodgepodge. This is not a fact in the hodgepodge, right? We already know this. We know that gravitational potential energy is m times g times h, and we know that a change in gravitational energy is m times g times the change in height, right? Let's imagine that I drop this, and I want to know how fast it's going when it hits the ground. I can calculate a change in potential energy by knowing a change in height. Now, what doesn't matter? What's something that doesn't matter? Well, let's say that I am measuring my distance from the floor, and I say, okay, this is 2 meters above the floor, something like that. Okay? It might be correct to say that this object is 2 meters below the top of the stairs. What if we call the top of the stairs our floor and measure everything from there? Do we get the right answer? The answer is yes. The answer is yes. It doesn't matter. And this is something really deep about physics and really deep about science, which you don't need to write down, but it's good to think about, is that the universe does not care how we choose to label it. Right? The universe is just the universe. It does not care about us, as far as I can tell. And it's just going to behave the way it's going to behave. And we are here stubbornly trying to figure out how it's going to behave. And it's always surprising us. But really importantly, it should not care how we choose to label it. And so if I said that this object was 2 meters above this floor, or if I said this object was 2 meters below that floor, both of those things would be correct. But notice that would give us different amounts of gravitational potential energy. One would be a positive gravitational potential energy, one would be a negative gravitational potential energy. But it turns out it doesn't change any of our answers. It doesn't change anything that we predict. You're going to do an activity in DL where you talk about this. And you're going to see that it doesn't matter. Now, why am I talking about this? This just sums up what I said. Right? It doesn't matter what you call the floor when potential energy. That means it's possible to have negative gravitational potential energy, which may seem a little bit weird. If you've thought a lot about what energy is, it may seem a little bit weird to think about the fact that you can have negative energy, but you can. You can have negative energy, and like I said, you will explore that more in DL. Okay, so this is the last fact in the physics hodgepodge. Saying energy is conserved in a system means that the total energy of the system is not changing. This we know, right? This is this one up here. Right? We've seen this before. There's no heat, there's no work. The energy in the system is not changing. But there's another way of talking about it. Why are we talking about it this way? I'll say that in a second. But there's another way of saying that same thing, and that's this sentence here. Let's say that I freeze time, and I look at my system, and I calculate all the energies in the system and add them up. And I get a number. Whatever that number is doesn't really matter, but I get the number. The number that I calculated, and then let's say that I press play again and let the system do its thing, and then I hit pause somewhere else. and then I go through again, and I calculate all the energies, and I get the number. Those numbers should be the same. Right? That's what it means to say energy is conserved. It means that the total energy of the system, in other words, the value of all the energies added up, is not changing. But there's another way, and so there's another way of talking about it that is the same thing. Right? These look different, but they actually mean the same thing. This is another thing you're going to explore in DL. Now, why am I talking about this? Why does this matter? Well, the reason is sometimes it is useful to think about things this way. Right? Sometimes it is useful to talk about energies this way because it's just really hard to calculate changes sometimes. Sometimes it's just hard to actually go through and use the equation for the energy to calculate its change. We're going to see an example of an energy that's like that next week or maybe the week after. Not sure yet. We're going to see an example of an energy where the equation is super complicated, and to calculate it, the change in energy would be basically impossible. Well, depends on how good you are with the calculator, right? But more difficult than we care about. And so sometimes it's easier to say this instead. Sometimes it's easier to say this, and you'll see why in DL this week and next week when we introduce this new kind of energy. Okay? It's also useful when we do something called, when we plot energy. So I've shown you a couple graphs of energies right here, right? I've shown you a couple graphs of energy. And we've seen a couple of these perhaps in DL. One of the topics that you're going to see this week is you're given a system and you're asked to plot what the energy looks like at a bunch of different spots. And I'm going to tell you from my experience teaching this course that is probably the hardest topic in the course. That's the thing that people struggle with the most, having graded a lot of quizzes with plots on them, having graded a lot of exams with plots on them. So you're going to spend some time on it in DL. I will talk about it more next week as well. But also there's a video on it, and so if you go to Canvas and you look at the short lecture videos for this week, the first one is plotting energies. And I strongly encourage you to try to watch that video before DL6. Before DL6. Okay? So you don't need to watch it before DL5, which is today or tomorrow or Wednesday, but before DL6. Okay, really quick. I just want to go over what we're going to be covering in DL and how this information might help you on a quiz or exam. So, first off, with mechanical energies, there are a lot of mistakes that are very easy to make with mechanical energies, that are not as easy to, they're much less likely when you're working with internal energies. There are a lot of little things, mistakes that are easy to make with mechanical energies, and I want you to see those, so that's why we're talking about them in DL, right? Those will help you avoid making the mistake on the quiz when it matters and when the points matter. Okay, there's one more slide after this. Conservation of energy. It turns out that there's a lot of things that we can learn about a system, even if we don't actually know what kinds of energy are involved. You're going to see an example in class. You're going to see an example in DL of a system where there's one type of energy that you know nothing about. But you're still going to be able to learn interesting things about it just by using conservation of energy. Right? That's how powerful conservation of energy is. Okay, last slide. The other thing you're going to be doing in DL, working with this new way of talking about conservation of energy. Again, it's the same thing. It's the same thing. It's not a new idea from physics perspective, but it's a new way of thinking about it that allows us to do some interesting things that we couldn't do before. You're going to see that in DL. That is going to be really important when we get to plotting energy. And I promise you, you will be asked to do a plotting problem on a quiz or one of your final exam questions. I promise you. So that's why this is important. And then the last two things. This one is working more with springs. Springs are a little bit weird, so you're going to work more with it. And then this one, this is the last thing you will do in DL6. And this is one of my favorite activities in the entire curriculum. This is a really good example of a quiz type problem that you're actually going to get the time to sit down and work through in DL with your friends. It involves pulleys, it involves strings, kinetic energy, gravitational potential energy, and all that kind of stuff. So you're going to build a model. It's a really cool model. I really like it. Maybe you don't think it's cool. That's fine. Remember, I don't care if you don't like physics. I can't make you like physics. I just hope that you, by the end of the quarter, you think it's not so terrible. But this is a really, really, really important problem in DL. You'll see it at the end of DL6. I strongly encourage you to pay close attention to it because it will help you on the quiz or final, I promise. All right. Have a great rest of your week. Like I said, I will try to turn around the quizzes by next week, and I will see you then.
For the people at the SBC.
Yeah, I'll about that.
Okay, sorry.
Yeah, no, that's my mistake.
No. It's
Well, no, but I did make a mistake. I forgot to include that piece of information on the quiz. So we know that that's a problem. We'll grade it knowing that, and we'll correct for that. So that yeah.
Thank you.
Hey. Yeah.
Are the slides going to be uploaded?
Is what?
The slides.
Yes, that was. Yeah, I meant to do. I totally forgot to do it. I'll do it as soon as I get back to my office.
Okay, thank you.
Yeah. Hey.
So I came from the SDC.
Yeah.
The problem too.
Yep.
You weren't given an
I know. I will send out a message about it. Yeah.
Oh, I had a quick question
Yeah.
about some of the grading for the
Yeah.
quizzes. So, like, let's say you get the 100% correct answer
Yeah.
with some of the